So in chapter 7, we're going to continue dealing with our different trig functions. But what we're going to do is really take an algebraic point of view of all this stuff. In 7.1, the goal is to simplify complex expressions that involve lots of different trig functions. And that might sound really intimidating, but it turns out it's not that bad. It's even kind of satisfying when you get to the stage where you can do this. So let me show you what I'm talking about. There's really two facts you're going to need to be successful in 7.1. The first one is what's called the Pythagorean identity. The Pythagorean identity tells you that for any angle t, sine squared of t plus cosine squared of t is equal to 1. It's a really nice identity and it allows things to simplify really nicely. If you're curious where it comes from, is the equation of the unit circle. So maybe you recall that the equation of the unit circle is x squared plus y squared equals 1. And because we define the cosine of an angle to be equal to the x coordinate on the unit circle and the sine of an angle to be equal to the y coordinate on the unit circle, informally the cosine of t equals x and sine of t equals y, we can take this equation and plug these two values in and produce the Pythagorean identity. You don't really have to concern yourself with the derivation, you just have to know this fact, that if you ever have the sine squared of an angle plus the cosine squared of an angle, it simplifies to just the number 1. The other fact that you'll need is the knowledge that you can express any of our 6 trig functions just in terms of sine and cosine. So as a reminder, our 6 trig functions are the sine of t, cosine of t, tangent of t, cosecant of t, secant of t, and cotangent of t. When we first introduced these, we defined the sine of t to just be equal to the y coordinate on the unit circle, and the cosine of t to be equal to the x coordinate on the unit circle. And then the remaining 4 trig functions were just ratios of the x coordinate on the unit circle, the y coordinate on the unit circle, and the number 1. So for example, tangent was y over x, cosecant was 1 over y, secant was 1 over x, cotangent was x over y. But if the sine of t is the y and the cosine of t is the x, and each of these remaining things just involve x's and y's, then I can rewrite each of these remaining things in terms of sine and cosine. What I'm saying is, instead of thinking about the tangent of t as the y coordinate over the x coordinate, where the y coordinate is the sine of t and the x coordinate is the cosine of t, we can kind of cut out the middleman and just say that the tangent of t is the sine of t divided by the cosine of t. Similarly, instead of thinking about the cosecant of t as 1 divided by the y coordinate, since the y coordinate is just the sine of t, we can think about the cosecant of t as 1 divided by the sine of t, the secant of t as 1 divided by the cosine of t, and the cotangent of t as the sine of t divided by the cosine of t. We've now written each of the 6 trig functions just in terms of sine or cosine. This one is just sine, this one is just cosine, this one's sine divided by cosine, etc., etc. So here's what questions look like in this section. You start out with some big mess, and that mess involves some combination of your various trig functions. Often things are squared, you got division, multiplication, addition, all sorts of different operations going on. And what you're supposed to do is simplify this thing. And what I will always ask you to do is simplify it to the point where you get your answer is just a single trig function. So your answer will be one of these 6 things that you see right here. I guess you can just guess and have a 1 in 6 chance. A common challenge students have with algebra is there's so many things that I could do to this expression. How do I know which one I should do? To try to alleviate that, what I'm going to do is I'm going to give you a series of steps that will always solve any problem in 7.1. Your first step is to rewrite all of your trig functions in terms of sine and cosine. What do I mean by that? If you stare at this thing, you see tangent squared and you see secant. However, a minute ago, we talked about how you could express any of your 6 trig functions, including tangent and secant, in terms of just sine and cosine. Your first step will just be to change anything that's not a sine and cosine into sines and cosines. Often doing so makes your problem really, really ugly. You get fractions inside fractions, that kind of thing. But don't worry about that. That'll be a problem for the next step. So in this specific example, what I could do is I could say, well, tangent squared of t is weird notation that really just means tangent of t squared. And tangent of t is just sine over cosine. So I can replace tangent of t with sine of t over cosine of t if I remember to square this entire thing. And then I have to add 1 for this one. And down in the denominator, I got the secant of t, but remember secant is just 1 over cosine, so I'll replace the denominator with 1 over cosine of t. My expression, as ugly as it may be, now only involves sines and cosines, so what that means is I'm done with step 1. My next step is to rewrite this expression to cancel common terms, and that's a little bit vague, but what I'm getting at there is if you stare at this thing, you see fractions inside fractions, for example. You have sums, you have things that are squared. What you want to do now is use your algebraic knowledge to rewrite this so that you don't have fractions inside fractions, so you don't have multiple terms. Put things together as best you can. So in this specific example, you might be like, well, I want to get rid of the fractions inside fractions, but I don't just have a fraction divided by a fraction. I have the sum of these two terms divided by this fraction. If the top were just a single fraction, it would be easier for me to divide the fraction on the top and the fraction on the bottom. Maybe I can make the top a single fraction. The way you could do that is you could think about sine of t over cosine of t squared means sine of t over cosine of t times sine of t over cosine of t. And if I multiplied those two fractions, the way I multiply fractions is multiplying straight across, I get sine of t times sine of t on the top, in other words, sine squared t, and cosine of t times cosine of t on the bottom, in other words, cosine squared t. I still have this plus 1. I'd like to combine this plus 1 with this term. Well, in order to combine fractions, I need a common denominator. The least common denominator is cosine squared t. Instead of writing a 1 here, I'm going to write cosine squared t over cosine squared t. First, convince yourself that this really is 1. Anytime you divide a fraction by itself, you just get 1. And then understand why you're doing this in the first place, because you want this common denominator so you can turn this all into a single fraction in the next step. I'm going to leave this denominator alone for now. I still have 1 over cosine of t. And now I can take advantage of the fact that I have the same denominator up here in the numerator. So I'm just adding up these two fractions. How do you add fractions? Well, you leave their common denominator alone. You just write that a single time. So my common denominator is cosine squared t. And you add up the numerators. So I have sine squared t plus cosine squared t from here and here. Again, I'm going to leave the denominator completely alone for now. So I have 1 over cosine of t. I've now managed to rewrite this as a single fraction divided by a single fraction, whereas before I had two different terms on the top. Now I just have this single term here. That's good news. I know how to divide fractions. All you got to do is multiply by the reciprocal of the denominator. In other words, take this thing and flip it upside down. So the fraction that was up on the top, I'm going to leave that alone, and then I'm going to change this division into this multiplication by taking the reciprocal of the denominator here, changing it from 1 over cosine of t to cosine of t over 1. I cannot cancel out these cosine squared t's because you can't cancel over addition, but I could cancel out one of these cosine squared t's and this cosine of t because you can cancel over multiplication. What I'm saying is this goes away and one of these goes away, which leaves me with just sine squared t plus cosine squared t divided by cosine of t. I think that's about as far as I can go in step 2. So what I now want to do is something that I'm going to refer to as step 2a. Why am I going to call it step 2a? Because what you'll see when you get the hang of these is you kind of do both of these steps at the same time. And what step 2a is apply your Pythagorean identity. So what I'm talking about there is, remember there were two key things in red that you needed for this section. One of them was the ability to rewrite any of your 6 trig functions in terms of sine and cosine, but the one I talked about before that was this Pythagorean identity, which just tells you that sine squared t plus cosine squared t is just equal to 1. So if you're ever lucky enough just to have sine squared t plus cosine squared t in your expression, you can just change that into the number 1. In this example, I am so lucky. Note that the numerator here is exactly sine squared t plus cosine squared t. So I can just change that into the number 1, and I get 1 over the cosine of t. The way this example worked out is I kind of did all of my algebra first, and then I applied that Pythagorean identity. But what you'll see as you get better with these is you kind of want to be looking for your Pythagorean identity all along. Way back here, it might have made sense to change this sine squared t plus cosine squared t into the number 1. That might have made it easier to simplify stuff. So really steps 2 and 2a are stuff you should be doing kind of in conjunction as you go through and solve these problems. I've changed this original mess, tangent squared t plus 1 over secant of t, into just 1 over cosine of t, into something that's much prettier. In fact, 1 over cosine of t is something that I recognize. Step 3 is to change your simplified expression into one of your trig functions. What I mean is we now have 1 over cosine of t. However, if you go up here, you might remember that secant of t is the same as 1 over cosine of t. So I can change 1 over cosine of t into secant of t. In a sense, you kind of come full circle. You start out with other trig functions, you change them into sines and cosines so that you can simplify all this stuff in step 2, and then when you're done simplifying, step 3, you kind of go back from sines and cosines into your remaining trig functions. The point of this example was to show that tangent squared t plus 1 divided by secant of t is the exact same as secant of t. Who knew? This is just one example, and you shouldn't feel like you can do any of these at this point. I think the key thing for chapter 7.1 is repetition. I just need to give you a bunch of examples and have you work through each one. And that's what I'll do in the next video. However, before leaving this video, I have to tell you one more thing. There are lots of different ways that you can write your Pythagorean identity. So for example, if sine squared t plus cosine squared t equals 1, I could subtract cosine squared t from both sides of the equation. and that would give me that sine squared t equals 1 minus cosine squared t. This is equivalent to this, it's just writing it in a different form. Similarly, I could take this expression and, I don't know, subtract 1 from both sides. And that would give me an expression that looks like this, which is also equivalent to our original Pythagorean identity, just written in a different form. The point is, if you have this equation here, you can manipulate this equation to make it look a little bit different. So when you're down here trying to simplify, don't just look for sine squared plus cosine squared. Look for things like 1 minus cosine squared or sine squared minus 1. Look for various combinations of sines and cosines and the number 1. The final thing I want to show you before ending this video is that a lot of books will present 3 different Pythagorean identities. So not just these ones where you subtract from both sides of the equation, but imagine if I divided both sides of this equation by sine squared. I'd divide this by sine squared and I'd get the number 1 because sine squared over sine squared would be 1. I'd divide this by sine squared and I'd have cosine squared over sine squared, but because cosine over sine is cotangent, well, that's not what I wrote here. I guess I'll have to fix that. There we go. Because cosine over sine is cotangent, if I divided this by sine squared, I'd have cosine squared over sine squared, which would be cotangent squared. And then if I'm dividing everything on this side by sine squared, I should divide this by sine squared. And because 1 divided by sine is cosecant, 1 divided by sine squared would be cosecant squared. This Pythagorean identity also implies that 1 plus cotangent squared must be the same as cosecant squared. Or if instead of dividing everything by sine squared, I divided everything by cosine squared, I'd have sine squared over cosine squared. And because sine over cosine is tangent, this would become tangent squared. Cosine squared over cosine squared would just be 1. And 1 over cosine squared, well, 1 over cosine is secant, so 1 over cosine squared would be secant squared. We get yet another equivalent expression to our Pythagorean identity. And this bottom one right here, if you had this memorized, would have made this original problem much easier, right? Tangent squared t plus 1, the numerator here, I could have immediately changed that to secant squared t. And then I would have secant squared t over secant of t. I could cancel one of the secants from the top and one of them from the bottom, and I would just get secant of t in a 2-step process instead of this multiple step process that I did here. We'd get the same answer and we can get there a lot shorter if we recognize that there were different forms of the Pythagorean identity. The advantage there is if you have more tools, often you can cut out steps in your process. The disadvantage there is you have to memorize a whole bunch more tools. For what it's worth, I think the easiest way to go about these is to follow these steps as I listed them in this video. This will be a method that will always work for you. And yeah, admittedly, sometimes there will be shortcuts if you can recognize other versions of the Pythagorean identity. But in order to be able to do that, you have to first know these different versions of the Pythagorean identity, and you also have to be looking for them while you're simplifying your problem, which for most students is something that's just untenable. As always, you should feel free to do these however you want, but what I will do is I'll always follow the steps that I listed here, and then if there's ever any clever shortcuts like this one that I just showed you, I'll make note of that after the fact.